everyone. In this video, I'm going to continue the discussion I started a few videos ago on how to use classes and object-oriented programming in C++. Just as a refresher, let me show you the code base we've been working with. So I've got these three files here, main.cpp, book.cpp, and book.h. Book.h has the definition for a book class. Okay, the book class is pretty simple. It represents some information that a book might have in order to describe it. So I've got a title, an author, and a number of pages for the book that are private. For my public member functions, I've got a default value constructor, an explicit value constructor, and a destructor. The destructor doesn't do much. It just says hello from Destructor because I'm not dynamically allocating any of my attributes here, my member variables. All right, then I've got the standard getters and setters, and I've got this nice little display utility function here that prints out the title, the author, the number of pages for a book object. All right, so what I want to do in this video is return to this little note I made in a previous video saying that we could dynamically allocate a book if we wanted to. And now is the time to do that and explain it. So I'm going to head to the bottom of main here just so I have some room to take some notes. And I'm going to make an initial comment here that there is two distinct implementations of dynamic memory allocation and objects. Okay, that's kind of ambiguous, so what do we mean? Well, the first option here is what I mentioned previously. That is, we can dynamically allocate a book object. Okay, so the entire book object itself will live in the heap. Okay, right now all these book objects I've made up here, HP3, HP2, etc., they live in a stack because they're statically allocated. But we could dynamically allocate a book object. In fact, we're going to do that really soon here. The second distinction related to dynamically allocated memory is we could dynamically allocate the attributes of a book object. Okay, so if we dynamically allocated the attributes of a book object, then the memory that stores the attributes could be in the heap. The book object itself could be in the stack if it's statically allocated, or in the heap if it's dynamically allocated. Okay, remember that a pointer stores a memory address, right? The pointer itself is a variable. It could be in the stack or the heap. Its memory address that it stores could be for memory that's in the heap or in the stack. Okay, so if we're going to use an attribute as a pointer to store some dynamically allocated memory to store an attribute, then we're going to say that that dynamically allocated attribute is in the heap and its memory address is stored in an attribute of a book object, and that book object itself could be in the heap or the stack. All right, I know there's a lot going on here. We're going to do some examples in order to help explain it. All right, so let's start with the first one. The first one's a little more straightforward. Let's dynamically allocate a book object. Okay, so I'm going to have a book pointer, and I'm going to call it, say, book, let's call it book, here we go. Little indecision right there. Let's do HP5 pointer, okay, because I'm going with the Harry Potter theme. I've got the first 4 books. So let's have a pointer to a book object that lives in the heap that stores information about the 5th Harry Potter book. All right, so let's do the EVC here, just so that I can initialize this with some values. So this is going to be Order of the Phoenix. We've still got the same author here, J.K. Rowling, and I don't know how many pages this has, but this was a quite large book. Let's say 600 pages. All right, so now I can do HP5 PTR. I can dereference and select, or I can do the arrow operator or the indirect member selection operator to dereference and select. And I'm just going to call display here so I can see this book. Now, I've dynamically allocated memory. I should have a delete to free that memory. I don't right now, so technically I have a memory leak, but that's okay right now. All right, so there's the output from display called for our book HP5 pointer that HP5 pointer points to. All right, so far so good. Now, I want to show you that since I've forgotten to delete this book that's in the heap, Okay, I'm going to show you a little tool called Valgrind that you can use in order to figure out if you have memory leaks in your code or not. Okay, so right now it's saying leak summary definitely lost 72 bytes. Like, darn, lost 72 bytes. Okay, really I want to see 0 bytes here. Now, if I do properly delete this, let me compile and run again. We'll see right there 0 bytes. Okay, so now I don't have a memory leak in my program. All right, so let's explore a little bit more about what's going on with the destructor. We now have a book that's dynamically allocated. So when relative to HP 1 through 4 is HP 5, that HP 5 pointer points to, going to be destroyed. Okay, so I'm going to head over to book.cpp and I'm going to customize this book destructor here. So right now it just says flow from book destructor. You can see it's being called 5 times, but how do I know which book is being destructed? So I'm going to print out the title here so we can see which Harry Potter book is being destructed and in which order. All right, so as we look at this output, let's remember that we're allocating Harry Potter 1, 2, 3, and 4 on the stack. We're allocating Harry Potter 5 on the heap, okay? So I'm actually seeing them be deallocated in reverse order of when they've been allocated. So I've got 5, 4, 3, 2, 1. Okay, let me comment out that delete statement so that we don't see HP 5 being allocated. Okay, it's gone. Memory leak, but that's okay for now. So what's happening? Recall that statically allocated memory is allocated in the stack. And the stack is called the stack for a reason. It operates like a stack data structure, which is a last in, first out data structure. So what that means is the last memory allocated is going to be the first memory deallocated, last in, first out. So we've got Goblet of Fire here. This is the last book object that I allocated on the stack. So it's going to be the first one out. Okay, so let's take a look at Sorcerer's Stone. Remember, this is a LIFO stack, last in, first out. Okay, so that means that the first in is going to be the last out. So book 1, Sorcerer's Stone, is going to be the last out. So they're deallocated in the reverse order that they're allocated. Now, let me take this comment out, and I'm just going to move this entire chunk of code, let's say between HP 1 and HP 2. So you can see that this delete statement is going to invoke the destructor for our HP 5 or Harry Potter number 5 book, independently of when HP 1, 2, 3, and 4 are deallocated, okay? So this is going to force an invocation of the destructor. All right, so here it is. Sorcerer's Stone, we print out Order of the Phoenix, and then we see hello from book destructor destroying Order of the Phoenix. Okay, so there's just a little example, a little insight into how these two different regions of memory work. Okay, so we're not going to see the destructor for a book that's dynamically allocated on the heap until we delete it. We're not going to see the destructor for any of our statically allocated objects in the stack until the function in which they were allocated in exits or returns. Then we're going to see them deallocated in the reverse order that they were allocated. All right, let's move this code back down here. All right, that's a good introduction to distinction number 1, dynamically allocate an entire book object. Now let's move on to number 2, which is the trickier of the two, where we can or cannot dynamically allocate the whole book object. That's irrelevant. What we're going to talk about is dynamically allocated individual attributes of a book object. Okay, perhaps we are growing or shrinking in size for the object. Perhaps this is part of, say, a linked list, and we're keeping track of the list itself, right, which can grow and shrink in size. So we've got a lot of dynamically allocated, say, head pointers or tail pointers and things like that. All right, so let's head over to book and take a look again at our attributes. None of these are very good candidates like the two previous examples that I just gave for dynamically allocated memory, but it's okay. It's a small demo example. We'll just kind of brute force it to make it work. So let's say that num pages is no longer going to be an int stored in the stack. Okay, this is now going to be a pointer to an integer stored in the heap. We're going to dynamically allocate our integer that stores the number of pages. You would think there would need to be a lot of other changes because of this one change here in our header file, but there actually isn't. So this is really kind of under the hood how our book objects are stored, the state of them. These member functions are all public and the constructors are all public. This is the interface at which the world interacts with book. So we actually don't need to change anything here. Okay, we have a nice layer of abstraction here that encapsulates our state so that people can use our state of our object without knowing how it's actually stored. That way they can't corrupt it, say, by accidentally forgetting to free one of our integers here. Okay, so I need to make some changes to book.cpp. So first off, our constructors. Num pages is now a pointer to an int. If I assign 0, this is essentially making it a null pointer. What I need to do is first dynamically allocate memory in order to store this integer. Now that I have a pointer to some 4 bytes in the heap, I can dereference that memory address in order to actually store a 0 in those 4 bytes. Okay, so remember, every time we have a use of new, we should also have a use of delete in order to free that memory. That's where the destructor is going to come in momentarily. All right, our EBC, we've got to do the same thing. This is another path to creating and initializing a book object. So it too needs to allocate its own memory and then dereference to get to that memory and assign this parameter n int value to it. Okay, now it's time for the destructor. Okay, so I wrote here, should release resources like dynamically allocated memory. And here is our moment to do that. We need to delete num pages when we're done with it. And we're done with it when this book object is about to be destroyed. Whether the book itself is in the stack or the heap, okay, doesn't matter. It's going to be destroyed at some point, as long as there's no memory leaks, right? It's going to be destroyed at some point, and we need to properly release our resources, like the memory that num pages points to. All right, what else do we need to change? Getters for title and author are fine. Num pages, though, is a pointer, so we've got to dereference it to get that integer out. Setters for title and author are fine. Setter for num pages, not so fine. We need to dereference what num pages points to in order to assign this new num pages parameter value to it. And then display, just need to add a little dereference operator here in order to get the int out. All right, so let's save it. I don't need to change anything in main because remember our public facing interface hasn't changed, just how we're storing the state under the hood, which is abstracted to any users of our book class. All right, so this is interesting. We've got a crash here and it says double free detected, double free detected. Okay, so it looks like when we were trying to free Chamber of Secrets, okay, that num pages, it's already been freed somehow, which is pretty odd, right? So let's take a look at Chamber of Secrets. So that's HP2. So here's HP2, okay, seems pretty isolated here. But down here on line 27, we are using the member-wise copy assignment operator in order to initialize line number 27, HP3. Now, here's the tricky part, and this is going to be explained in more detail in the next video. But here's the tricky part, okay? So right here, what's happening is we're actually invoking the copy constructor, but we haven't defined a copy constructor. So what's happening is a default member-wise assignment from all the values in HP1 over to HP3. Okay, when I say it's a copy of HP2, I mean it's a copy of HP2. So whatever memory address is stored in HP2's num pages attribute right here is being copied into HP3's num pages attribute. Okay, so remember how a stack works, right? We're going to deallocate in the reverse order we allocate. So that means that Prisoner of Azkaban, HB3, is going to be deallocated before HB2, Chamber of Secrets. So we're calling delete on that memory address that HB3 has a copy of, and then we try to call delete on that memory address again that HB2 originally allocated. So this is the problem child right here. So I'm going to comment it out. And I can make a little comment here. So problem, when num pages is dynamically allocated, why the mem address of num pages in HP2 is copied to num pages in HP3. HP3 is freed before HP2, so we get a double free detected when we destruct HP2 and call delete num pages. So what is the solution? The solution is actually to define something called a copy constructor, where we allocate new memory for num pages in HP3. Okay, so what's happening here, I'll just say it one more time, but I'll explain it more in another video, is we're creating a book, okay, right? We're defining a new book right here, HP3. That means a constructor is being executed, okay? We should have something called a copy constructor, okay? A copy constructor is where we, as programmers, define exactly how a copy should occur from one object to another. But because we didn't define a copy constructor, what's happening is the default behavior for this member-wise copy assignment, which, as the name implies, member-wise copy. Each member of HP2 is copied into HP3. And when we're working with pointers, that means we've got memory addresses. So we're copying memory addresses over, and that can be very problematic, as you can see here. All right, so let me save this and compile it again and run it, and now our program doesn't crash. Of course, we've lost Prisoner of Azkaban. We commented out, but at least we aren't crashing our code. So in a next video, I'm going to come back to this exact problem here, explain copy constructors, and something called the rule of three, And I think I'm gonna actually start to type it down here because it's so important. I don't wanna end this video with you thinking you can't just do something like this, you just have to comment it out. That's not true. You can do something like this, but you have to be aware of something called the rule of three. So the rule of three states that if you define any of the following, then you should define all three. So what are the three? So one is a destructor, which we had to define because we added a dynamically allocated attribute to book. The second one is a copy constructor. Okay, so that's what's being invoked right here. It's a copy constructor because we're creating a new book. We're trying to create that book by initializing it to values of another book. And then three is the member-wise copy assignment operator. So this would be an example of operator overloading. Okay, so let me just make a little note here. So like book HP3 is assigned HP2. Okay, this is an invocation of a copy constructor. And then here, let's say I just did HP3 is assigned HP2. Okay, this would be an invocation of member-wise copy assignment because I'm not actually creating a book, right? This line does not invoke a constructor like this line does. All right, so that's what we're going to start with in the next video is copy constructors and see how we can fix that problem that we had earlier. All right, I hope you learned a lot about distinctions when it comes to talking about dynamically allocated memory and books. And I hope you had fun kind of seeing that last in, first out stack of memory working for the destructors. All right, thanks for watching.